Nitesh here. I work in Samsung Semiconductors, and today I'm going to talk about the storage innovations which happened in last decades and which are happening right now, and the software stack which is being developed to support those kind of SSDs. Okay, so to begin with, I will be starting with the storage devices, how it progressed from hard disk to solid state drives, and from there the software stack. Someone was talking about IO Uring and those stuffs, how they came up into the ecosystem, how those IO Urings are being developed something like they are being added with some new features such as pass through, which will help to address the new set of SSDs I'll be talking later. The purpose of this talk, it's mainly about how the things are getting progressed from storage perspective, and from there it usually comes to Linux, and from Linux you'll be having user space libraries. Yeah, I think I gave brief info. It's mostly about the storage developments and the corresponding changes happening in open source software. So if you see the overall trend last decade, it was mostly about we moved from hard disk drives to solid state drives, and the recent ultra low latency SSDs. And if you see on the right side, it's mostly about the performance numbers, wherein we talk about throughput and latency. So there is a clear improvement over HDDs in recent developments, and to handle these type of devices, right? Like if you take a SSD, they were faster mainly because of two things. One was mainly they had a multi-queue capability, and they were directly sitting on PCI bus. So the earlier stack, which was mainly consisted of hard disk drives, they were optimized for sequential read-write kind of optimizations, and even the schedulers which were designed at that time, they were handling those things. But with the new set of SSDs, the complete architecture needed to be changed, and initially spdk came up with a solution wherein they exposed complete PCI registers to user space, and from user space people used to form NVMe devices and provide a block abstraction, and applications were demoed using those things. And recently they also got 10 million IOPS with the storage, the SPDK kit. And from Linux side, multi-queue was introduced, and a new multi-queue scheduler was added, and pooled queue support was added. Pooled queue support was mainly for the ultra low latency devices, wherein it avoided the context switch, and overall the performance was better. And the next step was, like, if you see the previous slide, it's more like at the end the bottleneck was libaio, wherein maybe from NVMe you have multiple queues, and now with block MQ you transfer the benefits of multi-queue to the upper layer. But still, when the user wants to consume those, it's about libaio, which was fastest at that time, and it still lacked some of the features. To address this, Jens came up with a design of IO Uring, where the formation of IOs were mostly async, and they tried to mimic the NVMe device in almost all possible way. And this also had a use of like this also made use of shared buffers, wherein kernel and user could have a common buffer between host and application and kernel. And with this, Jens was recently able to achieve 10 million IOPS with a single core. And to make it simpler to use, the liburing was added with a simplified kernel interface. And also it had a lot of test support, which could help to develop applications really fast. And these were about the initial SSDs. And if you see the SSDs, they were actually direct replacements for hard disk drives. and the cost was comparatively better. Like if you compare the uh, price GB to dollar conversions, but they do suffer from some of the issues, especially something called log on log problem, wherein from host you might be writing 4 KB, but internally it will be writing more data. So this happens because of the NAND limitations, where you can't overwrite before doing a erase. So initially, uh, uh, let's say if you want to write a location inside SSD, so from host you might be writing to location A, but device actually writes to location B, and it maintains a table such that the next time host asks for reading A, it will be reading it actually from B. So this creates two problems. One is maybe internally you are writing more data than you required, and for that you need to keep more storage inside the device. So this is called over provisioning, wherein you have physically more data than required for the SSD. And to solve this, the next solution was give more power to host. Like host will be having more power where they can keep the different set of data. So the next set of SSD, not exactly new SSDs, it was a feature which was added to SSDs called multi-stream, wherein along with the data, you could provide an intelligence, like something called stream ID, wherein the device will understand these set of stream IDs should be grouped together and they should be stored together. The idea here is when a garbage collection happens, similar group of data will be moved together and they will be invalidated together. And with this we had better WAF and GC was reduced, everything was fine. And like even there are some type of file systems such as F2FS which do support these features. And F2FS works somewhat similar to the way device firmware works. So, and the next set of SSD was ZNS, which gave still more power to host, wherein the host can decide where exactly which block you can read from. And this, since more offloading happened in host, this required lesser DRAM from the device side, and from device side, the cost was reduced. And this also addressed the multi-tenancy problem, wherein the SSDs usually don't like a load which is mixed. Like I have a data which gets erased more often, and there's some data which gets replaced very less. So if you mix these type of loads for SSDs, the lifetime will come down with this. HDDs usually doesn't suffer this, but yeah, with the added benefit of speed, we need to make some changes in host stack to address this one. So the initially ZNS support was added in Linux last year, and also to support applications and all the file systems such as F2FS also added this. But still XFS and BTRFS type of file systems, the work is still is in progress. And the latest thing which is happening in so SSDs are like if you see the trend, we are moving towards more data and more data processing in hosts and all. So these new type of SSDs tries to address that one by reducing the data and offloading things to device itself. Yeah, so if you see the traditional stack, you will be having a database, and the database will be using file system to access the files, and from file system we convert things to blocks, and from blocks the things comes to driver to the device. So at the end, like from user's perspective, he usually wants to read and write some objects, but when it comes to device, right, it gets split into blocks, and again the mixed load work which I was telling earlier, that will come into picture. And so to address these type of things, the new set of SSD, which is a KV value SSD, has a intelligence to understand the object itself. Like you can provide a key and value directly, and you can bypass the complete stack. So here the idea of bypassing stack came because the traditional Linux kernel block layer is mainly optimized for read and write. So this new set of and the next I will be talking about the new set of software which tries to address this one. And the another set of SSDs are computational SSDs, where you can offload the complete computation itself. Like earlier we talked about key value SSDs, right? They were more kind of fixed, the way you can communicate and all. With computational SSD you can even have your computational logic, like you might want to add some custom computation things, and you can program these type of SSDs for that. The advantage with these type of SSDs is you need not take the data from your storage drives to do a computations inside CPU and put it back. So you can directly offload those things, and SSDs are smart enough to handle that. But the problem here is, like, we at present the stack is not mature enough to address this. And if you guys are familiar with like adding any features in Linux, it takes a lot of iteration cycles, and if any feature is like, I'd say at the end it is to be like it if application wants to consume it, it has to trickle down in lot of layers. So initially, last month we added something called IO-Uring pass-through, through which you can bypass the traditional file system layer and block layer. So you can directly issue async commands using async commands using Uring pass-through, and the commands will directly go to NVMe commands. And the latest set of SSDs, KV and computational, can use this and start developing applications based on this. The last one was xnvme. This is a user space library which abstracts the below layer to the applications. Like, let's say if you're an application developer, you can just start using xnvme, and the below layer you can choose any backend, like let's say IO-Uring, spdk, ioctl. The advantage here is, like, if you have a backend which has some features which you are looking to use in your applications, right? You can just change the backend, and the application layer APIs will remain same. And yeah, I guess with this I would like to end it. It was I hope I could convey the latest things which happened in storage. And yeah, any questions?
Hi. What's the state of flash support in kernel? Like, are we adding support there for the flash devices?
Flash in the sense the SSDs or the normal raw flash you are talking about? Raw flash, I think MTD does add it, but with SSDs usually we put it like flash usually comes as part of SoCs, right? These are the enterprise SSDs which usually sits on top of PCI, and I think recently we are having even client SSDs which are coming in laptops. So the way both works are like they are completely different. So this is more towards the client and enterprise SSDs. So I have attached the links for all the open source stack which we are using at present.
Hi, one quick question.
Yeah.
So you covered xnvme, it seemed very interesting, but could you explain the internals of how xnvme works? Because it seems to cover a lot of platforms,
Yeah.
a lot of
Yeah, sure. So
interaction.
like if you take, like, let's from application point of view, right? like when you are developing applications, so for consuming storage, you will be using some interface. Maybe the traditional is read or write calls and all. Okay, and the next thing, if you want to consume direct only from NVMe devices, right? The SPDK also provided a platform. And if you see the overall architecture, you have multiple backends which you can use. Like there is a ioctl which you can use, libio, SPDK, and you can actually change from platform to platform. Like let's say you developed the application for Linux, and then you want to move to Windows. Again, from application perspective, you need to move the complete stack, right? So if you use the xnvme libraries, those porting things are done by xnvme. Okay, so you just develop applications for xnvme, and the down layer you can choose while compiling and all.
And just a quick follow-up question: how big of a change is to port my application to use XNVMe?
XNVMe libraries are pretty much documented. I have attached the link as well, xnvme.io. So they provide all the generic memory allocations, IO submission things, and there are a couple of talks as well. Okay.
Yep, thanks.